you have any questions on anything at all?
Can we go over I'm assuming we will, but the addition and multiplication tables for the problem that we ended up with? You told us to make them, but I was just struggling.
Okay. I don't remember which one I told you, but somewhere in here, I'm sure. How far did this thing scroll up? Apparently. This one. Yeah. Okay, cool. Yes. Now I remember. All right. Are you okay with the cosets? Those being the only cosets that we have? Okay. All right. So, and the addition table go okay?
Yeah, I was just confused on when it was 2x. I didn't know how that, if it would just be 0 then.
Yep.
Okay.
And why is that?
Because it's mod 2.
Yeah.
I just wasn't sure if the x affected it.
Nope. Not at all. This gets a little annoying writing plus I every time, doesn't it? Yes. So a lot of times what they'll do instead is, there's a couple of different ways that algebraists will attack it. Sometimes you'll we've talked about this before, when we did equivalence classes with a number, we'll put brackets around it. That's one way to do it. Or put a bar over the top of it. That's another way. Even another way, I'm going to write this off to the side because I don't really care, because this is such a stupid distinction. I hate it. So usually when somebody types up a polynomial ring, they'll use a capital X to denote the variable rather than a small x. And so then if you want to talk about equivalence classes, mod out by an ideal, then you'll use the small x. Of course, when you're writing it by hand, you can't tell the difference between a big X and a small x usually, which is why, and the reason why I hate it. But that's what would happen. So we had this polynomial ring, and we had this ideal. So you would see, if you saw this typed up in a paper, perhaps, you would see those as capital letters. And then when you do the cosets, you would do 0, 1, little x, and little x plus 1. So you wouldn't have to write all the plus i's on the end. I know, it's stupid. But no one's very impressed by that. Okay. Anyway, a lot of times, though, we won't write the plus I all the time. I would put a little bar over the top of that when you're talking about the equivalence classes. Anyway, but you're exactly right, though. When you add these together, everything is mod 2 for the coefficients. So when you do 1 plus I plus 1 plus I, what do you get? 0 plus I. And then 1 plus I plus x plus I. This is the x plus 1 plus I. And then what's the x plus 1 plus I plus 1 plus I? It's the x plus I, yeah, good. And really what we're doing is, if I do that one off to the side, say, when you do x plus 1 plus I, and, plus 1 plus I. You remember we add those two together, like so. But again, all of this operation here is taking place in Z2. And 1 plus 1 would be 0 in that case then. So that's why that's just the x plus I. So going out the rest of the table here, when you do x plus I plus x plus I, what do you get?
0 plus I.
Yeah, you get the 0 plus I, because the x plus the x would give you the 2x. But 2 is the same thing as 0. So that's why that one's going to be 0 plus I. I'll try to do that old one. Thank you. And then x plus I plus x plus 1 plus I is going to be 1 plus I. Good. And then we should be able to fill out the rest of these. Notice the last when we do the x plus 1 plus the x plus 1, you get 2x plus 2, but the 2 is the same thing as 0. That part okay for the addition table? Okay, cool. All right, multiplication. Multiplication is a little trickier. Well, like I mentioned before, though, 0 times anything, no matter what ring we're in, that one's pretty universal, that we'll get 0. And the 0 of this particular ring is 0 plus I, so I can fill those out pretty quickly. We can also fill out the next row and column pretty quickly as well. 1 is the multiplicative identity in Z2 of X. So 1 plus I will end up being the multiplicative identity in the quotient ring. This is, by the way, we're defining our multiplication, right? We define multiplications of cosets by the coset generated by the multiplication of the representatives, right? So we can see that pretty quickly. This is just going to be the multiplicative identity as well. I guess I was putting parentheses around that to emphasize that I had that as a distinct coset. So now comes the trickier part when you start multiplying x's, right? So remember our ideal was x squared plus x plus 1. Right? Okay. Pardon me. So when you multiply x times the x, do this off to the side, x plus I times x plus I really is the same thing as x squared plus I, because I just multiply the coset representatives. But that's not one of the distinct cosets that we recognize, right? So I need to figure out which one of the 4 it really is. So again, remember I told you that when you mod out by an ideal, when we do create this quotient ring, we really are treating this thing like it's equal to 0. What I mean by that is, if I take the coset generated by x squared plus x plus 1 plus I get the same thing as the coset generated by 0, because x squared plus x plus 1 is in the ideal, and so is 0. And so they're equivalent to each other. So since they're equivalent to each other, when we mod out by I, or consider the quotient ring R mod I might as well just think of x squared plus x plus 1 being the same thing as 0, and that helps me simplify some things. So if x squared plus x plus 1 is 0, what could we say x squared was the same thing as? Negative x minus 1, but we're doing everything mod 2, so negative x is the same thing as, x, and negative 1 is the same thing as 1. So this is just going to be x plus 1 plus I. Does that make sense? Let's do the other one, because then we can fill out the rest of the table pretty quickly. If we do x plus I times x plus 1 plus I, again, we do this by multiplying coset representatives, right? That's the same thing as x times x plus 1. or x squared plus x plus I. Again, that's not one of the ones in the list, right? Not one of the ones in our list. So, pardon me, what can we replace it with using that same idea that we talked about before?
X plus 1 plus x.
Okay, x plus 1 plus x.
So just 1.
Just, yeah, it's 1 plus I. Good. Yeah, so notice that, again, if we think of x squared plus x plus 1 as being 0, I can move the x squared plus x to the other side, and since we're doing everything mod 2, plus and minus are the same thing. Negative 1 and positive 1 are the same thing, mod 2. So 1 is the same thing as x squared plus x, so this really does turn out to be 1 plus I. So what do we get for the last one? There's only one more multiplication we have to do.
Just x plus I.
Yep, I agree. So when we multiply, you would get x squared plus 2x plus 1, right? When we take the x plus 1 times the x plus 1, that's just normal everyday multiply it out, right? What is this part right here equal to? That one's 0, right? Because it's mod 2. And then you have x squared plus 1. Again, looking at this equation, x squared plus 1 is the same thing as x. So we really do get x plus I there. Is this okay? What kind of a structure do we call this ring, by the way? Notice that every non-zero element has a multiplicative inverse, and it's commutative. So what kind of a structure do we call that? Even better. So integral domain is just don't have zero divisors. Commutative ring with identity with no zero divisors. No non-zero zero divisors. This one's even better. Everything has multiplicative inverse, so it's a little bit better. So what?
That's a quotient ring.
Oh yeah, it is a quotient ring. That's just by definition. Yeah, that's how he created it. Actually, this one's, well, technically it is.
Field.
That's the word I'm looking for. It's a field. Yeah. Remember, field is everything has multiplicative inverse. Commutative ring with everything having multiplicative inverse. Remember, if it's not commutative, then we refer to it as a division ring. All right. So this is a field. This is a finite field. It has 4 elements in it. Turns out, I'm just going to mention this off to the side here. Turns out that every finite field has to have a prime power order. So 2, 4, 8, 16, 3, 9, 27, 81, 5, 25, 125, 625, so on up the line. But if it's a finite field, it has to have a prime power order, and the characteristic always has to be that prime. Remember that if your characteristic is not prime, then it can't be an integral domain. We talked about that before. If you have every integral domain has prime characteristic or a 0 characteristic. Because again, if it's composite, then you can split apart 2 elements and make them multiply together to give you 0. But this is actually a way to create your finite fields. We're not going to go into it too much, but notice that if I look at the polynomial x squared plus x plus 1, if we have time at the end of the semester, we'll talk a little bit about being able to factor polynomials. Because you talk about that in algebra class in high school, right? So we'll be able to talk about that a little bit more and go into a little bit more depth than what we would talk about in high school. But in particular, if it's a quadratic and it factors, what would each factor have to, what type of polynomial would each factor have to be? It would have to be linear, right? I just split it into 2 linears, correct? Remember that x minus something is a factor if that something is a 0 of the polynomial, right? That's kind of your factor theorem that you did back in algebra class, right? If I have a number that I plug in and I get 0 out, then I know that x minus that number is a factor of it, okay? Well, there are only two possibilities for zeros in Z2. They are 0 and 1, right? That's all they are. What do you get when you put 0 in for x into that polynomial? 1. What do you get when you put 1 for x into that polynomial? Which reduces to 1, right? So if I put 0 in, I get 1. I put 1 in, I get 1. So this polynomial doesn't factor. So in Z2 of x. So this is what we refer to as irreducible in Z2 of x. When it's irreducible, we can, it turns out that this particular ideal, we're actually going to talk about this today, this particular ideal cannot be properly contained in another proper ideal. And so when we mod out by it, we end up with a field. So we can create fields this way. So for example, if we do, if I can remember what numbers I need to use, let's consider Z3 of x. Let's say R is Z3 of x. And I is the ideal generated by x squared plus x plus 2, I think works. So first I want to claim that that particular polynomial is irreducible, just like I just talked about a little bit before. So you plug in 0, you get, not trick question 2, yeah. Put in 1, what do you get? For mod 3, 1, right? So plug in 4, we get, or plug in 1, we get 1. Plug in 2, we get 2, right? Because 2 squared is 4, so it's 8. Then mod 3 is 2, right? So this doesn't have any zeros in Z3. So this is also irreducible. So what we can conclude is, and I'm going to mention this, we'll talk about this later today, that R mod I is a field. You don't have any reason why you would expect that to happen right now. We'll talk about it a little bit. I think we'll get to it today. It may be Tuesday. See, I didn't push it too far down the semester. Okay. How many elements will this field have? Now, you might be able to guess without actually doing any work and then doing the reasoning. Let's go back up to the previous example. Previous example, we had Z2 was the field that we were considering, that our polynomial coefficients were coming from. The degree here is 2. And we ended up with 4 elements, right? I just told you a little bit ago that every finite field has to have prime power order. So what do you think might be the order of this one? Should be hopefully 2 obvious guesses. I literally am looking for a guess here, right?
6.
Is that a prime power order?
9.
Okay, 9's a good one. What would be the other one that might be a prime power order, given what I was just looking at before? 3's another good one. What else? Maybe 8 would be another one. So I got 2 and 3. I could reverse the rules, right? Okay. Turns out that it is 9. Let's think about why it's 9. What did I tell you to treat this as when we're doing the quotient ring? What did I tell you to treat this thing as? 0, right? So if I treat that as 0, your x squared turns out to be, what, 2x plus 1? It'd be negative x minus 2. Negative x is the same thing as 2. Or excuse me, negative 1 is the same thing as 2 mod 3. Negative 2 is the same thing as 1 mod 3. So what does that tell me? Every time that I see an x squared, I can replace it with 2x plus 1, right? Anytime I see an x squared, I can replace it with 2x plus 1. So if I can always get rid of higher powers of x, I really only need to look at linear polynomials, right? I only need to look at things that look like a plus bx plus I, right? Those are the cosets that I need to look at. Because anything that I see with an x squared, I can replace with 2x plus 1. So I can always knock it down to an x to the first power and or an x to the 0 power, a constant. Right? Where do the a and the b come from? Well, we're doing polynomials in Z3. So how many choices do you have for a? Do you have a question, Devin?
After this, yes.
Okay. How many choices do you have for a? 3. And how many choices do you have for b? 3. So how many total choices do you have for cosets? 9. Yeah, 3 times 3. So it is really a 9. Yes.
I think I missed something. How did you pull 2x plus 1 is equal to x squared from that as the 0?
Agree with that?
Yeah.
Okay, we're mod 3. So negative 1 is the same thing as 2, and negative 2 is the same thing as 1. Yeah, that's where I came from. Yeah, it's okay. I know, it's weird to get used to, right?
Yeah, I don't know why. I just hadn't processed it.
No, that's okay. So we would get 9 elements here. So this actually creates a field of 9 elements. If you wanted to create a field of 25 elements, you would use Z5 of x and then look for an irreducible quadratic. If you wanted to create a field of 343 elements, you would use Z7 of x and find an irreducible cubic, and so on up the line. It's a way to create these particular finite fields. I can see by some looks that you like, who cares? These finite fields have applications to coding theory, keeping information secure. So there are different coding mechanisms that are based in finite fields. So that's why people care. I mean, that's not why people cared when they were first discovered, but it turns out that they had applications. But the only reason why I'm even really mentioning it, except for the properties that we'll talk about when we do a ring mod out by a particular type of ideal. The reason why we care about finite fields is because they really are used in keeping information secure. There are different coding mechanisms based on those things. And you might still like, I don't care. I'm not going to do coding theory, but that's okay. You don't have to care. That's allowed. Yes.
Did you get the a plus bx plus I? Did you get that from the fact that the x squared is equal to 2x plus 1?
Yeah, so I got that from the fact that my x squared could get knocked down into a linear polynomial. Okay. Yeah, that's exactly right. That was where that came from. And honestly, when you're doing these finite fields where you do, if you want a prime squared or a prime cubed, you can literally just look at the polynomial, a quadratic or a cubic, and see that it has no roots in the finite field. Once you get to quartics and above, it's harder because I need an irreducible polynomial, which means it can't factor at all. Now, if you have a quadratic, and this is important for if you're going to go teach algebra, which is what I'm going to talk about it now. If I factor a quadratic, it has to factor into a linear and a linear. If I factor a cubic, it has to factor into linear and quadratic, and then maybe the quadratic factors, right? So quadratics, if they reduce, always have to have a linear piece, right? Cubics, if they reduce, always have to have a linear piece. Is that the same thing for a quartic, a fourth degree? No. You can factor a fourth degree polynomial as a quadratic and quadratic, and maybe those don't reduce anymore. For example, if you were looking at x to the fourth plus 13x plus 36, x squared. 13x squared plus 36, how does that factor?
X squared plus 9, or
Yeah.
x squared plus 9, x squared plus 4.
There you go. Yes, I picked something I would hope would factor, right? Okay. Does your x squared plus 9 and your x squared plus 4 factor any more in the reals? No. Right. You need complex numbers to get it to factor anymore, right? So this polynomial, pardon me, that polynomial is certainly reducible, but it doesn't reduce into any linear pieces at all over the reals. Okay. So it's a little bit showing that quartics and cubics and such are irreducible or a little bit trickier. So like I said, if at the end of the semester we have a little bit of time, we'll talk about how we can do that in some certain cases. All right. In any event, are we okay with this example now? Okay. All right. So, let's see. We were talking about quotient rings. Did another example of a quotient ring here. Let's see if we can tie some of this now to homomorphisms. So, you've already talked about this particular this particular set of things. So we'll let F from R to S be a homomorphism of rings. Then the kernel, and a different kernel than what we were talking about earlier before class, the kernel of F is, your book just uses a K. I don't know why I'm using F because usually I use phi anyway. Your book just uses K, but the standard notation for kernel is KER. So the kernel of F is the set of all things in your domain that map to 0 in your codomain. Yeah, we're talking about kernels and linear algebra. Same idea. Yep. I believe one of your homework assignment problems at some point was to show that the kernel was an ideal. I think. I'm sure I assigned something along those lines. I think I just called it K and said everything that mapped to 0, didn't call it the kernel. Yeah. So it was one of your homework problems, right? So I won't reprove it. Theorem, the kernel is an ideal of R. And the reason why you need a homomorphism, of course, is because you need to break up over you need the fact that it breaks up over differences and breaks up over products to get to the fact that it's closed under subtraction and closed under or absorbs multiplication. So you get your ideal piece. Turns out that we can use the kernel to help us get isomorphisms. This is referred to as the first isomorphism theorem. So I'll use F again, since I just had F up there, although I don't particularly like using F, but I see it in the book and then I write it down. Let F be a homomorphism. This one actually says surjective in the book. That's not necessarily it's not necessary if I state this correctly. With kernel, I don't even need to say with kernel. Just let it be a homomorphism. Sorry. Then, when I take R and mod by the kernel, this is isomorphic to the image Oops, I forgot the letter R. The image of F. Remember what the image is? It's a set of all outputs. So it's basically the range. Set of all possible outputs. Basically the range. Just call it the image, and I'll use IM for it. The book states this as a surjective homomorphism, so it just wants to use S. So before we prove this, pardon me. Before we prove this, let's see if we can use it with an example or 7. Okay. All right. Let's say your ring R is Z and your S is, let's say, Z6. Can you find me what I'll say is an obvious homomorphism from R to S? Hopefully it'll be obvious. And I want it to be surjective. I want to hit everything in Z6. So can you think of a function that could map any old integer to something mod 6? What might you do? If I do that, what will happen in Z6? That will give you a homomorphism, but what will that do to every element? If I map it to 6 times the element and then do it mod 6, it'd be just 0 all the time, right? So instead of doing that, what if I just take the number and mod it by 6? Your example works as a homomorphism. It just doesn't land onto what I wanted. That'll certainly give me onto, right? Certainly not 1-to-1, but it is onto, correct? Now, going back to what you said, though, what is the kernel? Are we familiar with this notation, by the way, that I use with the little arrow with the vertical piece on the front? Rather than saying f of x equals x mod 6, it just says x gets mapped to x mod 6. That's all that means. We okay with that notation? Okay, cool. All right, what's the kernel? What things get mapped to 0? What things? Was that?
R times 6.
Yeah, it's anything that's a multiple of 6, right? The kernel of f here is, pardon me, the set of, we'll say 6n, where n is an integer, right? It's the multiples of 6. Do we have a name for that ideal? Well, that was what kind of, right? 6z, or the ideal generated by 6. That's another way to write it, right? The principal ideal generated by 6. Agree? So here's what the first isomorphism, sure it does. The first isomorphism theorem says. It says if you take your ring and mod out by the ideal, it's isomorphic to the image. So when I take the integers and mod out the ideal generated by 6, I get the integers mod 6. Which kind of makes sense, right? Because again, when I said we write it this way, what did I say to treat the elements in the ideal like? They're equal to. When we mod out by an ideal, we treat the elements like they are. What did we do when we were making those tables earlier? We treated everything in the ideal like they were 0, right? And what do you do when you mod out by 6? You treat any multiple of 6 like it's 0. Yeah. Same idea. Kind of makes sense, right? Conceptually, if you think about it that way. Yeah. Okay. Let's see if we can do another one here. Pardon me. This is number 3. This one is not as an explicit example. Goodness. But it's an idea that's kind of important as far as fields go. It says if f is a field, R is not just the zero ring, so it's an actual non-trivial ring. And our function, this time I will call it phi, from F to R is surjective, then phi is an isomorphism. Assume that I'm talking about homomorphisms and not just a function. So I've got a field mapping onto a non-trivial ring. Okay? That's what surjective means, right? It's onto. So I'm not just mapping everything down to, say, 0. Okay? We want to prove that phi is an isomorphism. Well, how can we show that phi is an isomorphism? So let's think about a couple of things before we get there. And this is more of a conceptual idea that I don't know why I said conceptual. Weird. It was conceptual. Let's talk a little bit about the conceptual stuff here. All right. So if F is a field, what are your possible ideals of a field? Well, what's an ideal of any ring, no matter what the ring is? The 0. Okay. What's another an ideal of the ring, no matter what the ring is? It could be nothing but 0, or it could be everything, right? So we could certainly have just 0, or we could have absolutely everything, right? As the two possibilities. Okay. Well, what about in general, though? We know that for general rings, there's typically more ideals, right? For example, in the integers, any multiple of an integer gives you an ideal, right? But what about a field? Everything but 0 is what kind of an element in a field?
Non-trivial.
True, but what kind of other element? I talked about this earlier. Every element has an inverse. Every non-zero element has an inverse, and we call those elements the what of the ring? The units, right? What did we say earlier happens if a unit gets in your ideal?
It's just everything.
It's everything, right? If a unit gets in your ideal, it blows up to the whole ring, correct? So can I have any other ideals in a field besides the trivial ideal in the whole field? No. Because if I try to make it bigger than 0, the only things that are outside of 0 are the units. Once a unit gets in there, everything gets in there, right? Because the reason why is because ideals absorb multiplication. If a unit's in there, then a unit times its inverse is in there, or 1 is in there. And once 1 is in there, all hell breaks loose, right? Everything gets in there. Okay? So there are only exactly 2 ideals of any field. Sounds like a good true-false question, right? Right? But we understand why, correct? If you try to throw anything other than 0 in the ideal, if you're throwing a unit in there, units are bad for ideals. They make them blow up. Okay. All right. So let's go back to the example. We know that the kernel is an ideal. So what are your 2 possibilities for kernel?
0.
Yeah, 0 in the whole thing, right? Well, what happens if your kernel is the whole thing? Remember, the kernel is a set of everything that maps to 0. So if your kernel is all of the field, what's your map? What did everything get mapped to? 0, right? So if the kernel of F, of phi is F, then phi is just the 0 map. Right?
Can you explain that again? Sorry. Why is it just a 0 map?
So if the kernel is everything, and the kernel is a set of everything that maps to 0, then everything maps to 0. Yeah. I just needed to say it a different way. Yeah. The kernel's everything, and it's a set of everything that maps to 0. So everything maps to 0. Is that what we have in this situation? No. Okay. It says that we have a non-trivial ring and it's surjective, so it's not the 0 map, correct? So the kernel of phi here must just be 0. Now this does tie back to linear algebra stuff. Remember when we had a linear transformation, I know it's been a while. We had a linear transformation and we had the kernel was nothing, or just the 0. Then we had a 1-to-1 transformation, right? We already know this thing is onto. So if the kernel is 0, then we should have something that is 1-to-1, right? I'll think of it another way. What kind of thing would you have if this is not anything that has to do with field? If I take a ring and I mod out by the 0 ideal, I treat 0 as 0 and nothing else, what should that be isomorphic to? Did I actually do anything if I modded out by the 0? It's just R back again, right? I didn't do anything, did I? All the cosets of the 0 ideal are just all the elements of R. Okay? Right? Okay. So going back over here, if I think of, if I do F mod out by the kernel of phi, by the first isomorphism theorem, that has to be isomorphic to R. But what did you say the kernel of phi was? Well, it was just 0. So F is isomorphic to R, which is what we wanted to show. So phi really had to be an isomorphism. And in particular, if your kernel is 0, then the homomorphism is 1-to-1. Let's show why. Do this off to the side because this is not too bad. If kernel of phi is just the 0, then phi is 1-to-1. How do we show something as 1-to-1 again? How do we show something as 1-to-1? Hip tried to get out. That was not good.
Suppose an element in the outputs find the input.
That's onto. Suppose you have 2 outputs that are the same? Yeah. Okay. And then show that the R1 had to equal the R2, right? Okay. All right, we're given something about the kernel. Several years ago, I had a student, every time I'd say kernel, he would just start laughing. I don't know why, but his laugh was like a donkey bray. So it was, everyone's like, it was really weird. And then, of course, everybody in class would start cracking up because Dan would start braying like a donkey. Anyway, it was really funny. All right.
Funny word.
What's that?
Funny word?
Yeah. All right. So anyway, we're given something about the kernel. Kernel says something about all the things that map to 0. So if I start with those images, how can I introduce 0 into that equation? Yeah, subtract 1 over to the other side here. Why am I using F and I used phi? What is my problem? Well, do we have all day? I can tell you lots of problems, but sorry about that. My bad. And now it won't scroll. There we go. All right. We were subtracting it over to one side, right? Is what we're doing? Okay. What kind of a thing is phi? What kind of a function from rings is it? Well, yeah, okay. But in particular, when we're talking about mappings of rings, we usually want them to be what kind of things? It starts with an H. There we go. So how can I using the fact that it's a homomorphism, how can we rewrite the left-hand side? Good. So now I've taken phi of something, and it equals 0. So where does that something live? What set does that mean? What set does that live in? Well, generally speaking, it's equal in the what of the homomorphism? It mapped to 0, so it is in the kernel. Good. Right? That has nothing to do with anything except that's the definition of kernel, right? It's the set of things that map to 0. But what are we assuming about the kernel? It's the I0 ideal. So what does it say that R1 and R2 must be? Or what does it say R1 minus R2 equals? Start there. 0 or R1 equals R2. This is what we wanted, isn't it? Yeah? Okay. So, and actually this is an if and only if. We only did one direction. 1-to-1 if and only if the kernel is 0. Right? Okay. The other way is even more straightforward. What element of the ring always maps to 0 in the codomain? What element in your domain always maps to 0 no matter what the homomorphism is? 0 does, right? If it's 1-to-1, you already have 0 mapping to 0. Can anything else map to 0? No. So that's why your kernel is just the 0 element. Okay. All right. In any event, we can use, this is the idea behind the first isomorphism theorem, is that you can find isomorphisms a little bit more easily if you can just find surjective homomorphisms and know what the kernel is, rather than having to go through all the work for isomorphism. All right, so let's do a couple more examples here with this. Let's look at number 8. Number 8 has R and S are rings. We'll use pi maps R cross S to R by pi of R comma S is R. First thing it asks is, what is the kernel of pi? Almost. You're right. In a sense, you're right. It's not quite just S because elements in your domain are ordered pairs. So it's not quite S. What would it be?
0S.
Yeah, it's got 0 comma S for all S and S, right? So your kernel, but you actually got to the whole point of the problem when you said just S. Good. Your kernel is the set of all 0 comma S such that S is in S. Good. The problem asks you to show that the kernel actually is isomorphic to S. Why is your kernel isomorphic to S? Can you find me a function that goes from the kernel to S, or vice versa? I could go the other way. I can go from S to the kernel. That is going to be 1-to-1 and on to and be a homomorphism. Yeah. Take 0, s to s, right? We agree? I don't think it's too bad to show that's going to be 1 to 1. Well, certainly not going to be too hard to be showed that's onto, right? If s is an s, use 0, s to map to it. So showing that it's surjective is pretty straightforward. The kernel, the things that get mapped to 0 are 0, 0. So the kernel is just going to be 0, 0. So then you'll get their isomorphic to each other. So the idea behind this, of course, is that when you do R cross S and mod out by the kernel of this pi, you should be getting something that's isomorphic to R. Now that doesn't seem very exciting at all, but let's think about the notation now and why this might be a little bit more that looks like algebra that you've done before. This class. This is bad, by the way. This is not the right notation for this because one set doesn't live inside the other. But the kernel of pi is the same thing as S, essentially. It has the same structure, right? So on the left-hand side, I've got R times S over S. What do we have on the right-hand side? R. I'm using equals on purpose. This isn't really what we have, but this is kind of what we have, right? I take R times S and I divide out by R, I get S, which algebraically makes sense for what you've done before, right? So even though we're kind of doing weird things, the properties of algebra that you've known still hold. Now again, this is not the right notation. The reason why it's not the right notation is because subsets of R cross S have to be ordered pairs, then this isn't, right? So this is bad notation. And what else? These are cosets and these are elements in R. So really they're not the same elements. That was why we use isomorphic instead. But from a structure standpoint, they're the same, which is what we're interested in. It's not what names did we give the elements. It's what structure does the set have. And they have the same structure, which again looks exactly like what you've done back in algebra class, well before you took this algebra class. Anybody's thinking I'd rather go back to the old algebra class. All right. What's that? That's okay. That's allowed. It's absolutely okay. All right. Let's see. What else do I want to do today? Oh, let's look at number 21. This one wants us to show that if I take the integers mod 20 and mod out by the ideal generated by 5, I get something that's isomorphic to the integers mod 5. Now, now notice, the thing that's on the left-hand side is a set of cosets. Rather than trying to first figure out what the quotient ring looks like, and then figure out a well-defined function from the set of cosets to Z mod 5, that is 1-to-1 onto and a homomorphism, let's ignore the factoring part, the quotient ring part. Let's just look at Z20 and Z5. Okay. Let's first find phi from Z20 to Z5. Let's do that first. We have integers mod 20 and I want to map it to integers mod 5. What might you do with an integer mod 20 to map it over to an integer mod 5? Mod it by 5, yeah. Yeah. That's certainly going to be surjective without any issues, right? The elements in Z5 are 0, 1, 2, 3, 4, and you certainly have 0, 1, 2, 3, 4 over in Z20. So surjective is not a problem. Making sure that it really is a homomorphism might be a little more challenging, because I can't just do this from any old Z mod something to Z mod something. I need kind of that division property, right? 5 goes into 20, right? So for example, what I mean by that is if you just did something like Z6 to Z4 and did X goes to X mod 4, pardon me, 0 certainly gets mapped to 0 without any question, right? 2, there's a 2 that is that the right number I want? Yeah, let's do it this way. 2 gets mapped to 2. And what else? I just want to make sure I do this right. Oh, yeah, this is right. 4 gets mapped to 0 is what I started with. We agree with those? Right? What should phi of 2 plus 4 equal? Yeah, it should equal 2, right? But what is 2 plus 4 in Z mod 6? Yeah, it's phi of 0. Is that equal to 2? No, phi of 0 is always equal to 0, which is not 2. Right? So I can't, if I don't have that divisibility property, this isn't going to work. This does work because it is divisible. You can go through the work to show that it really does work because it's divisible. It has to do with just the modular arithmetic piece. Okay. You have to be a little bit careful. I'm not going to make that particular function does not work as a homomorphism. In any event, we should check this really is a homomorphism. It's certainly surjective. That's not a problem, right? It's clearly surjective. 0, 1, 2, 3, 4 is in Z20, so you get it in Z5 as well. What's the kernel? What gets mapped to 0? 0 and 5, and what are the things in Z20 mapped to 0? Well, 20 is 0. There you go, 10 and 15, right? Which is the multiples of 5, right? In Z20, right? So the first isomorphism theorem says that if I take Z20 and mod out by the kernel, I get something that's isomorphic to the image. Oops. Is it okay? Let's do another one. Actually, let's go back over to this example with the Z6 to Z4. I can't make it onto Z4. However, I can make a homomorphism out of this. So let me cross this out. Let's take X to 2X mod 4. In this case, what does everything get mapped to? What are your two possibilities for outputs? Two and zero, right? Either you're going to double something that's odd and get 2, or you're going to double something that's even and get 0, right? All right, so your image, in this case, if I call this phi, will be 0, 2, right? The ideal generated by 2 in Z mod 4. What's the kernel?
Even numbers?
The even number is mod 6, right? So 0, 2, 4, which is just the ideal generated by 2. So again, by the first isomorphism theorem, if I take Z mod 6 and mod out by the ideal generated by 2, I get something that's isomorphic to the ideal generated by 2 in Z4. Notice those are two different 2's, by the way. But notice, you should show that it's a homomorphism. I have been kind of skirting past that. You should show that it's a homomorphism, but notice it's showing something that's an isomorphism here doesn't require as much work. I just need to find a homomorphism that's onto and figure out what its kernel is. And then I get an isomorphism for free by the first isomorphism theorem. That's the idea here. Is okay? Yeah. All right, let's do another one here. This is number 11. I never did. I still need to go back and prove the first isomorphism theorem. I haven't done that yet. Let's say you've got a mapping from Z, we say Z adjoin root 2. Remember, that's polynomials in root 2, but when I square root 2, I get 2. So really, I just get an A plus a B root 2 thing, right? Remember that structure? Let's define this by phi of A plus B root 2 equals A minus B root 2. What do we call that when we change the sign in the middle, by the way? Conjugate. Good. Yep. All right. So, is this surjective? Let's do that first. Do I have a surjective function? I ain't worried about homomorphism yet. Do I have a surjective function? Do I hit everything in Z adjoin root 2 by doing conjugation? If I just take an arbitrary element in Z adjoin root 2, what do I use to get mapped to it? What maps to 7 plus 5 root 2?
7 minus 5.
Yeah, what maps to negative 3 plus 8 root 2? Negative 3 minus 8, right? We just use the conjugate, correct? So this is certainly surjective. We agree? You just have to flip the sign on the output. Okay. We should show it's a homomorphism. I don't think that's too hard to see because you'll just combine your terms with the root 2's in it, right? And make sure the sign flips like it's supposed to. Okay. So this is a surjective homomorphism. I'll leave the details of the homomorphism to it's just a matter of playing around with the algebra, right? Pushing the symbols around. Okay. All right. What's the kernel? Well, let's think about the kernel. Remember, the kernel of phi would be the set of everything that maps to 0, right? All right, so if I start with phi of r is 0, well, your r looks like a plus b root 2, right? So what are we really setting equal to 0? A minus the b root 2, yep. All right, and then so the hint in the book says that you can assume that 2 is irrational. You would need that a, which is a rational number, it's an integer, is equal to b times the square root of 2. Well, can I take a rational number? What kind of a number do you get when you take a rational times an irrational? Irrational, right? Rational times irrational has to be irrational, right? No matter what. The only way I can do, unless that rational number is what? What's the only way I can do this multiplication and make a rational number out of it? What would you need to multiply by to make a rational number out of it? 0, right? It's the only way to make it rational. So since square root of 2 is irrational, we need a equals b equals 0 for this to be true. So the only thing that's in the kernel there we go. So the only thing in the kernel is 0. So what does that tell you about the function if the kernel is 0? The function is, well, the function itself is if the kernel is 0, the function itself is 1 to 1. All right. So we really have an isomorphism, correct? We have an isomorphism from the ring to itself. When we have an isomorphism from a ring to itself, we refer to that as an automorphism. Automorphisms pop up in lots of different places. But in particular, automorphisms pop up in a field that's referred to as Galois theory, which we're definitely not going to get to later this semester. Okay. However, Galois was a French mathematician who was also highly involved in the French Revolution. I believe. That's right. Anyway, it doesn't matter. Worked on... What's that? Pretty much. He also died in a duel, but that's okay. At 21. But anyway, Galois theory looks at what are referred to as automorphism groups of fields, which this is, if you change the z root 2 to a rationals root 2, that still works. Do the conjugates of a rational, you get an automorphism. In that whole field of algebra, pops out being able to solve any polynomial equation with real coefficients. What I mean by that is we have a quadratic formula, right? All should know quadratic formula. If you've taken history and math, you probably talked about Cardano's formula, which talked about solving cubics. There's also a formula that solves an arbitrary quartic. Unfortunately, when you get to the 5th degree, it's not solvable anymore from a formula. Okay? And that's where Galois theory pops in. Yeah. So that's actually tied to this type of function, where you've got a field getting mapped to itself. And notice that when I do conjugation here, by the way, that part doesn't change, right? The A part doesn't change, that stays the same. So if I take, in this particular case, if I take something that is purely an integer, it maps to itself, right? So under that homomorphism, we refer to that as being fixed. So Galois theory has to do with what are the fields that are fixed under automorphisms and looking at the different automorphism groups. So anyway, it's the only reason why I wanted to mention it, that even though we're doing something that looks kind of silly, it actually does have applications outside of this class. In particular, it has applications to saying, don't ever try to find a formula for solving an arbitrary fifth degree polynomial because you can't. Or anything higher. So this really does have applications to stuff that we've talked about in other classes, even though it doesn't look like it. All right. Any questions on that at all? Oh, there's a lot of words today. Well, let me give you some problems to work on, because you wanted some problems to work on, right? Of course. So let's see. This is on page 159 and following. What do I have on here? I want you to turn in 6, 10, 16, and 17.
Remember back when we did 3 problems? Way back then?
Way back when? This isn't going to be due till a week from Tuesday, though, since we don't have class next Thursday.
Oh, I forgot about that.
Yeah.
That's gonna save me a lot of headache.
Right, so this won't be due till like a week from Tuesday. I believe we do have a test scheduled that following Thursday, though.
That's not good.
We'll survive. All right.